This is a slide introducing the initial and final value theorem for Z-transform. Given f of z, if we want to find small f of 0 in time, what we can do is that we take f of z and let z tends to infinity. You will see that the z minus 1 is all sitting at the denominators of this expression. By letting z tend to infinity, we're left with f of 0. Hence, this is the way to get f of 0 from f of z, by letting z tends to infinity. In the final value theorem, what we can do is to find f of n as n tends to infinity is to multiply f of z by z minus 1 and letting z tends to 1. We will not prove this, we'll just state this property. Now, you must be careful when you use final value theorem, because in certain f of n, it will never stabilize, it will never converge to a constant value. In such a case, when fn does not converge, then the value you found using this expression will be wrong. So use this expression only when f of n has a final value, and it is only for causal sequence. So for this property to work, you must check that all the pole of z minus 1 times f of z are inside the unit circle, with the only possibility that the pole is at z equals to 1. We'll now use examples to show how we can use initial and final value theorem. Right, on the left hand side, we have a unit step. A unit step, remember, is a sequence that has 1 from 0, 1, 2 until infinity. So by observing what the time sequence u of n, we know exactly what is f0 and f infinity. They are both 1 respectively. Let us use the property. We set z tends to infinity for f of z. So this goes to infinity, this goes to infinity. This is not the correct way because it's infinity over infinity. What we should do is we divide both by 1 over z. And when that happens, we'll get 1 minus 1 over z. Setting this to infinity, this becomes 0. So it's 1 over 1. Answer is 1, which is exactly what we have predicted when we observe un anyway. What about f infinity? Well, we take z minus 1 multiplied by f of z and letting z equals to 1. So what happened? You cancel z minus 1 and you're left with z. You set this to 1, so the answer is 1. So the initial and final value theorem works for this sequence. What about sine pi over 2n? In this sequence, we know that it is a sinusoid and it is spinning as n continues. It has a constant value at f of 0 because we can substitute n equals to 0. Sine pi over 2 is answer 0. We can also get this using the f of z. This is f of z for the causal sequence sinusoid, and setting z tends to infinity. Well, so what do we do? Again, we multiply by 1 over z on the top and bottom. So this becomes 1, this becomes z, this becomes 1 over z, and letting z tends to infinity, this goes to 0, and it is 1 over infinity, and hence it is value 0. So we are okay with f of 0, but for f of infinity, remember this is a sinusoid and he's spinning all the time with n. So, well, let's anyway plug in what we are expecting. Z minus 1 multiplied by z squared plus 1. When we work it out, it looks like the answer is 0. But This is incorrect because we know that sine pi over 2n continuously oscillate. So why doesn't this work? Why is this wrong? Because we didn't take care that there is a pole not outside but at the unit circle. So let's look at this. Z squared plus 1, when we want to break it into roots, is z minus j, z plus j, z squared minus cj plus cj minus j squared is equals to z squared minus 1 is plus 1. So the root is at minus j and plus j, and this is exactly at the unit circle. So because there is a pole at the unit circle, that is why we cannot use the final value theorem for this. That's all. Thank you.